Okay, so let's do a quick review. Okay, so the first thing we did was we took some base, let's say maybe it looked like this. Okay, I'm going to get my husband to check this thing out because this is acting funky. Uh-oh, that's not what I want. I want that. So we have some base, and then we're standing on top of it, some cross-sectional area. So who knows what the cross-sectional area looks like? Maybe the cross-sectional areas or semicircles. Okay, so the cross-sectional areas could be semicircles, cross-sectional areas. Okay, so we could have something like this. All right, where these are the cross-sectional areas. Okay, so for volume by slicing, you had to determine the cross-sectional area. And then you had to integrate it. Okay. Then we did volume by disk. So for volume by disk, we have some region. Okay, so we have some region. Here's my region. A and B, that's not dark enough. A and B. And then we revolve the region about the x-axis, choose a value, find our disk, find the radius of the disk, and the volume is the integral from A to B of pi times whatever the radius is squared dx. And if it's revolved around the y-axis, then you have something that looks like this. Here's my region. It gets revolved around the y-axis. I find a y value, draw my disk, and my volume is the integral from C to D of pi times whatever my radius of y is, dy. Okay. Then we did volume by washer. And with volume by washer, we have two functions. So we have the area between two functions is revolved. Okay, and you will see a washer. Okay, so you may have something like this. Here's my region. Maybe I have one function that looks like this. And I have another function that looks like this. And I'm going to revolve it around, let's say I revolve it around this line. So now I'm going to have something that looks like, these things are always hard to draw. Okay, so when I revolve it, okay, go on. Something doesn't look right. That's because that's too close. Here we go. That's better. Okay. And so I choose my value here, and then I find my first circle. Then I find my second circle. There's my washer. So my volume, the integral from a to b of pi, I'm going to have a big radius of x squared minus a little radius of x squared dx. And about the y-axis, I get the integral from c to d of pi times my big radius of y squared minus my little radius of y squared dy. Okay, so again, volume by washer. Then we had volume by shells. So cylindrical shells. And this is the one where you see a soda can. Okay. Doesn't matter what the region looks like. We did not do this one. This one's a good one. We did not do one like this. Okay, so we now grab our X, rotate that thing. There's my shell. So I now need to get the volume, the integral from a to b of 2 pi times whatever my radius is. As we know, the radius we have to find the radius and we have to find the height. Okay, so we did that. Then we did arc length. So the length of a curve L, so given y is equal to f of x and a less than or equal to x less than or equal to b, the length of the curve, the integral from a to b of the square root of 1 plus dy dx. Some people write f prime. I don't care what you write, but it's the derivative squared dx. And given x equals a function of y, c less than or equal to y less than or equal to d, then the length is equal to the integral from c to d of the square root of 1 plus dx dy squared dy. Okay, so that's what we've learned in this module thus far. Okay, where are we going tomorrow? Okay, so let's just suppose for a moment. Now we want to talk about surface area. Okay, now all these volume problems gave you a volume. Surface area is just what is used to make the soda can, not what the soda can holds. Okay, so let's say I have something of this length. Okay, so this length is, say this length is little l. Okay, so that's the length of that little piece. And I want to revolve that thing around a particular axis, or I revolve it around a line. So let's say I revolve it about this line. And when I revolve it about that line, it's going to show up on this side. I can find a value in between. And when I revolve it, the only thing I'm getting is the outer shell. Okay, because I'm not revolving a region, I'm revolving a line. So not revolving a region. So I won't get volume because I'm only revolving a line. I will get surface area. So I will get this, and I will get that. So now the surface area is simply going to be 2 pi times the radius of this thing times the length L. So I have a radius of this. Okay, so my radius is whatever the radius of that thing is, R. And that is the length of that. So if I cut it, flattened it out, I'm going to have a rectangle. Okay, well now suppose I have something that looks like this. So now I'm going to take this line I'm going to rotate it about an axis. So when I rotate it, I'm going to get something that looks like this. And then I'm going to rotate it. And I want to find its surface area. So here's my little piece. So we want to find the surface area. Well, the surface area again is going to be 2 pi times the radius, which, as you can see, the radius is going to change depending upon which x I'm at. So if I'm at this x, I'm going to have this radius. If I'm at this x, I'm going to have that radius. So my radius is going to change. And then I need this length. But I already know that I can find the length of this thing by taking 1 plus dy dx squared. So I'm going to get the square root of 1 plus dy dx squared. And if I integrate that thing from a to b dx, that is the surface area. And that is where we will pick up tomorrow. Okay. All righty.
Dr. Lott, may I ask, I missed out on something that you mentioned before class started.
Okay, hang on.
Mr.
Gotcha.